Hi there. This is the third and last video in section 5.2, covariance and correlation. To begin with, let capital X and capital Y be random variables with joint PMF little p or joint PDF little f. So in this video, we will actually not be concerned with derivations using either of these things, but since this is where covariance, expectation, so on and so forth are derived from, we'll assume there's some underlying PMF or some underlying PDF. Also, we can define two new random variables from the old random variables capital X and capital Y given as follows. Z is equal to H of XY. Similarly, W is equal to G of XY. And this defines two new random variables. So from last time, we recall that the expectation can be defined for these random variables defined in terms of capital X and capital Y, and the expectation operator turned out to be a linear operator. And so what does that mean? That means that the expectation of a linear combination is the linear combination of expectations. Last time we also defined the covariance operator. So given that we have any two random variables, Z and W, that are defined in terms of the random variables capital X and capital Y, we can define the covariance in the following way. It's the expectation of the following product. So from last time, we derived these three properties, which will be important in today's video. So one is that the covariance is a symmetric operator, meaning that the covariance of Z comma W is the same as the covariance W comma Z. So they can switch order. Two is that the covariance operator is linear in the first and second component, meaning that the covariance of a linear combination in the first component is the linear combination of covariance in the first component, where the second component remains the same. So it follows this algebraic manipulation. Similarly, the covariance operator is also linear in the second component, fixing the first component. Finally, number three is that we found a generalization of the variation of X, or in other words, covariance is a generalization of variance in the sense that covariance of X comma X is just the variance of X. And this doesn't have to be an X. That could in fact be any such random variable defined in terms of X and Y. So we could have, probably would have been more appropriate to emphasize that these can be Z's, where Z is any such random variable defined in terms of capital X and capital Y. We'll see that these properties hold not just for random variables in terms of X and Y, but in general. But since we've derived all these from having a joint PDF or PMF of two random variables, that's what we'll stick with. There's one more important property that I would like that we did not derive, and this is the following. The covariance of the random variable Z with any constant C is equal to 0. And this is true for any constant C. So C itself defines a random variable, the constant random variable. And to see why this is true, we can see this immediately by noticing that the covariance of Z comma C, by definition, and the expectation of a constant is just that constant. So this is just C minus C, which is 0. So therefore, expectation of 0 is again equal to 0. making number 4 true. So using these 4 properties, we'll be able to derive a number of results today about covariance. So proposition 1, we have a shortcut formula very similar to the variance shortcut formula. The covariance of our random variable z, w defined previously is given by the following. Expectation of the product, subtract the product of expectations. And so this is a proof directly. We'll do a direct proof. So the covariance of z, w is by definition given by this product. We can multiply or expand this product to give us the following. We have the following expanded. So expectation is a linear operator, so we can apply it over this sum, giving us the following. So we have the following, so these 4 pieces. So now using again linearity of the expectation operator, we can have the following. So the first term remains the same. Now for the second, we can notice that expectation of w is a number or a scalar amount. And since expectation is a linear operator, we can factor out expectation of w. Leaving behind just expectation of z. So we have expectation of w times expectation of z. Similarly, and then finally, the expectation of a constant is that constant, which we've seen before. So this is just like so. And the last 2 cancel each other out, leaving behind the following. Expectation of the product, subtract the product of the expectations. So using this fact, we also get the another way to conveniently show the following. So covariance is a generalization of variance in the sense that variance of x is covariance of x comma x, and the following equation follows directly from the above generalized shortcut formula for covariance. So what are some things about covariance? So we talked a little bit about in last video how covariance is related to the linear relationship between capital X and capital Y. or in this case, just two random variables defined in terms of capital X and capital Y. So let's say that capital X and capital Y have very large covariance. Does that mean that they're linearly related? And the answer is not necessarily. So for example, suppose that capital X measures the weight of particular objects, and let's say that this measurement is in micrograms. And let's say that Y measures the volume of these objects, and let's say that these are in micrometers cubed. So in other words, capital X and capital Y tend to produce very large numbers. So in other words, when capital X and capital Y are very large in magnitude, it's possible for the covariance of those two random variables to be very large. However, capital X and capital Y may not have a very strong linear relationship. So because of the scaling, or the fact that the units of measurement might be very small, in other words, our random variables are very large in magnitude, we define what is called the correlation coefficient. So this is very much that related to the covariance operator, except it accounts for this scaling problem, and it's defined as follows. So the correlation coefficient between two random variables, capital Z and capital W, so this is in general, not just with X and Y, but with Z and W as defined before, is denoted by rho sub Z comma W, and this is equal to the following operator. It's denoted by correlation, or capital CORR, so with a capital C, of Z comma W, and it's given by the following. It's the covariance of Z comma W, but scaled by the standard deviation of Z and W. So again, standard deviation is the square root of the variance of each. So it's defined just like so. So unlike the covariance operator, this is not going to be, we don't expect this correlation operator to be linear or bilinear in each component. However, we can still derive a lot of results about the correlation operator using our results of the covariation operator. So what are some properties of correlation? So one, which is very nice, is that the coefficient rho sub x comma y is defined between -1 and 1. So in other words, the correlation between two random variables, capital X and capital Y in this case, the correlation is defined for any random variables defined in terms of x and y. But in x and y in particular, this will always be falling in between -1 and 1. Another property is that if x and y are independent random variables, then its correlation coefficient is equal to 0. Hence what we call uncorrelated. Now it should be noted that two random variables can be uncorrelated, however, not independent. In other words, being uncorrelated does not imply that x and y are independent. So remember, our correlation coefficient tells us how closely x and y are linearly related. So x and y may still be related, but just not linearly. In other words, have a 0 correlation coefficient and yet still not be independent. However, if x and y are independent, then they have a 0 correlation coefficient. And finally, number 3 tells us that if the correlation coefficient is plus or minus 1, if and only if y is equal to a linear function of x. So recall, if and only if is the following double implication. In other words, the left-hand side is a condition, the right-hand side is a condition. And the left-hand side is true if and only if the right-hand side is true. So what is this saying? It's saying that the correlation coefficient tells us something about x and y. It's how closely they are to being linear functions of one another. It obtains the maximum value of plus or minus, so maximum in magnitude, of plus or minus 1 if and only if y is in fact a linear function of x or vice versa, and is equal to 0 in the case that x and y are completely independent. So correlation coefficient's very nice for determining this sort of linear behavior. So the last proposition that we're going to do in this video is we're going to give a proof to the following. Is that even though the correlation operator is not a linear operator or bilinear operator, it follows that we have the following result. The correlation of a linear function of x together with a linear function of y is equal to the correlation between x and y. And this is somewhat sensible, or what we'd expect, because if correlation measures how closely two random variables are being linear, then linear functions of those random variables should be the same amount or closeness to being linear. So this will also be a direct proof. This will be given by starting on the left and working our way to the right. So to begin with, and it should also be noted here, which I forgot to write down actually, is that either both A and C are positive or both A and C are negative, and neither are 0. So this is going to be an important fact for us. Otherwise, you actually end up with a plus or minus 1 up here. So we have to make this assumption, which will come up later. So starting on the left, by definition, it is the covariance of the following. Divided by the product of the square roots of these corresponding variants. So on the top, we're actually going to do 2 steps here. The covariance is bilinear. So distributing the covariance over each of the following, we get the following. Each of the following arguments, that is, we get and this distributes into the 4 components. So this makes sense that there's 4 different terms in the same way that when you multiply 2 binomials, you get 4 terms. So this follows from distributing the covariance over each of the arguments one at a time. When you do that, you end up with the following 4 terms, and getting from this step to this step, I will leave as an exercise to the reader. In the bottom, we recall from section 3, chapter 3, that the variance of a linear function of x is the following. This is just the square root of the a can come out, but it becomes squared, and the constant goes away. Similarly, variance of y. So using our one property that we showed at the beginning of the video, in other words, property 4, the covariance of any random variable with a constant is equal to 0. And that's true for any constant c. It follows that all of those terms must be 0. So now, pulling the a and the c out of the square root, we get the following. We have this following. Now, this is where we must use the assumption that both a and c are greater than 0 or both a and c are less than 0. If both a and c are greater, in this case, that they're of the same sign, their product must be positive. Therefore, these terms cancel out. Giving us the following. And by definition, this is the correlation of x and y. It should also be noted here that there was nothing in particular about x and y that we needed. This could be, we could generalize this proof to actually just using z and w here, because as this entire proof works for any two random variables defined by capital X and capital Y. But in short, we just used x and y here. So these are all the results that we'll be looking at in this section. So this wraps up correlation. And in the next video, we'll be starting section 5.3 and 5.4.